Hi, Professor. We are from Team Reinforcex. I am Rishita Pakam and my teammates are Narsimha Reddy and Sai Teja. And now we are going to present our research titled Reinforcement Learning for Game 2048. Let me begin introducing our topic. 2048 it is a strategic puzzle game where players combine number tiles to reach 2048 tile or higher. It serves as a real world analogy for decision making under uncertainty, similar to challenges in business strategy and resource allocation. For example, planning routes in traffic where every choice can significantly impact the outcome. In both the game and the real life, every decision matters, making it an ideal environment for applying AI. In this project, we evaluate four AI strategies to determine which performs the best. By comparing these methods, we gain insights into how AI can enhance decision making and provide solutions for complex real world problems. Let's now look at our research question. In our research, we hypothesize that an AI agent utilizing reinforcement learning methods like Q-learning and temporal difference learning can effectively play the game 2048 by selecting optimal moves to maximize the score, achieve tile values of 2048 or higher, and minimize decision time compared to other strategies like expect max and baseline approaches. Now let us see about the related work. For our review, we have reviewed three literatures. These researches on 2048 has explored methods like Q-learning and TD learning with improved reward systems and adaptive learning rates, as well as heuristic approaches like Expectimax using depth-limited searches. While these studies focus on individual methods, our work differs by implementing and comparing multiple strategies within the same game environment. This helps us to compare their performance, computational complexity, and learning efficiency, giving a better understanding of the strengths and weaknesses in making decisions. Coming to the AI strategies that we followed to implement our research, 2048 game environment follows simple rules where players combine number tiles to maximize their score and reach the 2048 tile or higher. The game starts by randomly placing a 2 or 4 on the grid, and players move tiles in one of the four directions up, down, left, or right, merging matching tiles in the process. To solve this, we implemented four AI strategies. The random agent served as the baseline model, making random moves without strategy. Q-learning uses reinforcement learning to improve decisions by learning which moves works best over time. TD learning predicts rewards dynamically after each move. Finally, the expect max algorithm uses a heuristic search evaluating possible moves through a tree-based approach for strategic decision making. Now let's look at the random agent code. This code served as a baseline model for evaluating Q-learning, TD learning, and Expectimax. As the game count increases, it will take a lot of time to execute. So I'm initializing the game count as 10 and running the code. So we can observe that we got average score of 1026, standard deviation, and the frequency for reaching each of the tiles. This code simulates multiple games of 2048 using a random move strategy to analyze the performance. For each game, it initialized 4x4 grid, executes random moves until the game ends, and tracks the scores and highest tiles reached. After all the games, it computes and displays the average score, standard deviation, and frequency of reaching specific tiles. Coming to the results, for 10,000 games, the random agent achieved an average score of 958.71 with a standard deviation of 470.36. While it consistently reached lower value tiles like 16 and 32, its success rate for reaching 256 tile is just 4.15%, highlighting its inability achieving higher tile values. Moving forward, Nasima will continue.
So coming to Q learning, in our project, the agent was evaluated the after state of the board after each move. It used a reward system to update its Q values, focusing on maximizing scores and reaching higher tiles. The balance between exploration, which is nothing but trying new moves, and exploitation, choosing known best moves, was crucial for improvement. If you look at the performance across different iterations of games, for the first 1,000 games, the average score we got is 2,499.96, and the success rate for tile 512 is 4.76. So as the number of iterations increases, the average score increases and the success rate of reaching tile 512 increases. Let us see the demonstration of Q learning. So for the time sake, we use less number of games. Training games was initialized to 10, evaluation games initialized to 13. We can run the code. So it clearly gives the average scores of each game and standard deviation of each game and the tile reach frequency. So coming to temporal difference learning, our temporal difference learning agent assessed the board state after each move. It predicted the expected future rewards and adjusted scores incrementally using a learning rate, leading to faster convergence compared to Q learning. This method allowed the agent to make smarter moves dynamically. If you look at the performance across different iterations of games, for the first 100 games, the average score we got is 3208.08, and reaching the tile 512 has a success rate of 14% and tile 1024 has a success rate of 0.12%. We can clearly see that compared to Q learning, TD learning has a highest tile reach, which is 1024. So as the number of games increases, we can predict average score increases and standard deviation of the score increases. So coming to code demonstration. So the number of training games was initialized to 10, test games was initialized to 13. Let us run the code. So we can clearly see the statistics here. Average score, standard deviation of score, how often the agent reached the tile. We can clearly see highest tile was reached over here, which is 512. So let us go to Expectimax. Expectimax, it is a heuristic search algorithm. As we know that our Expectimax agent recursively evaluated moves using a depth limited search. For each move, it considered the potential placement of new tiles 2 or 4 and the player's response aiming to maximize long-term scores. Depth levels control the computational complexity over here. For each depth level, we use the same number of iterations, which is 5. So performance across different depth levels is listed in below figures. So at the depth one, the average score we got is 15,883.56 and reaching tile 2048 has a success rate of 0.1. So in Expectimax, we can clearly say that highest tile reached is 2048. As the depth increases, highest tile reaching highest tile 2048 is increases and the average score also increases. We can clearly see that at the depth 3 we got 40,389.76 average score. So coming to code demonstrations. So for the time being, we initialize depth equals to 1 and we get the average scores and standard deviation and of course the tile values at each iterations. We can clearly say that 5 iterations are recorded here and tile values and of course the standard deviations of scores. So coming to next slide. To summarize this, from this comparison, Expectimax emerged as the strongest performer, but its high computational cost makes it less feasible for large-scale applications. TD Learning offered a balanced approach, achieving consistent results with lower computational demands. Q Learning demonstrated promise, but required extensive training. The random agent, as expected, served as a benchmark for comparison. With that, the rest of the presentation will be continued by Saiteja. Thank you.
Coming to the limitations, the first one is high computational complexity. The Expectimax algorithm achieved the best result but required significant computational resources due to its depth-limited research. And next, dependence on extensive training. Q-learning and TD learning agents improve their performance over time but require playing thousands of games to converge to an efficiency policy. The reliance on the extensive training data highlights the challenge of scalability. So sensitivity to parameter tuning. Both Q-learning and TD learning required careful tuning of parameters like the learning rate and discount factor to achieve optimal performance. Limited scalability. The developed agents were specifically designed for the standard 4x4 grid of 2048. Scaling to larger grids or applying the same techniques to other games would require significant redesigns. So these limitations highlight the constraints of the methods implemented in our project, emphasizing the need for future work to address these challenges and make the agents more efficient and adaptable. Next, coming to the future scope of the project, advanced techniques for enhancing learning. So in this project, Q-learning showed promise but was limited by its reliance on a Q-table. So future scope includes replacing the Q-table with neural networks to handle the exponential state space of larger boards. Expect max optimization. So future improvements include pruning techniques to reduce unnecessary computation and evaluations to prioritize promising moves. Adaptability and scalability. The AI agents developed in the project were trained on the standard 4x4 2048 grid. So to extend their usability, they can be adapted to handle larger grids, which involve more states and more decisions and real world applications. So the decision making frameworks developed in this project can be applied to other domains like robotics, logistics, and healthcare. Just like the agents choose optimal moves in 2048, similar techniques can guide robots in navigation and task planning. So TD learning could optimize resource allocation in supply chains by predicting outcomes of various actions. Coming to fine tuning parameters. So during the project, Q learning and TD learning required careful parameter tuning. For the future work, it involves like automating the process using optimizing algorithms to find the best parameter dynamically, improving efficiency and reducing manual effort. So we conclude that in our project, we evaluated performance of 4 AI agents: random agent, Q-learning, TD learning, and Expectmax. So among these, Expectmax was the best performer frequently, achieving the highest tiles like 2048 and beyond due to its strategic depth limited search. So TD learning and Q learning showed steady improvements over the random agent. The random agent performed the worst due to its lack of strategy. Overall, our project highlighted the trade-offs between computational complexity, learning efficiency, and performance, offering valuable insights into designing AI agents for solving strategy-based games like 2048. So this conclusion ties together the project's outcomes, challenges, and broader implications, showcasing the value of the work done and the opportunities for future advancement. Thank you.